In this particular segment, we are going to deal with a topic known as matrices. So let us first define what is a matrix. So matrix is the singular and matrices is the plural. So a matrix is a rectangular arrangement. A matrix is a rectangular arrangement of numbers or terms in form of horizontal rows and vertical columns. Okay, so now let's really understand what this means. Let us underline some important statements in this definition. First of all, it's a rectangular arrangement, okay, meaning you are going to have a few elements in horizontal rows. So rectangle is a two-dimensional object. So you are going to have horizontal rows and vertical columns, right? And the terms or the objects that you are going to arrange, they can be either terms, algebraic terms, or they could be numbers, which means they could be either constants, or they could be variables, or they could be functions, or they could be certain operations, and so on. So such an arrangement in form of horizontal rows and vertical columns where a number of terms or constants are used, such an arrangement is called a matrix. Matrices are always represented by capital letters. So assume that the matrix A is given by, and matrices are always enclosed within such brackets, right? So if I were to write the elements inside this particular matrix, the elements could be half, 0, root 3, 5, minus 1.8 and x square, right? Now you will notice here that there are two rows. The horizontal arrangement is called the rows. So over here you will notice that there are two rows. This is row 1 and this is row 2, and there are three columns. The vertical arrangement is called columns. Okay, so this particular matrix has two rows and three columns. So let's mark the columns as C1, C2 and C3. So this particular matrix has two rows and three columns. Therefore, we will define the order of this matrix as 2 by 3. Now, please understand that this is not multiplication. It is the symbol for by. So, don't simplify 2 into 3 as 6 over here. What it means is I always write the rows first. So, the number of rows is 2 and the number of columns here is 3, which is why the order of this matrix is 2 by 3. Now your matrices could have any order. The order could be 1 by n till n by 1, or it could also be in a square form and so on. So we will now see all different types of orders that you can have. But let us quickly define the order of a matrix. So the order of a matrix is always denoted by the number of rows by number of columns, and it is an important property that a matrix has. There are many operations of the matrices which will depend on this order. So we need to understand this concept of order really well. So now let us try to write a few matrices and let us find out their order. And let us also learn about some special types of matrices. Let us take a look at the four matrices that have been listed here. The matrix A is, you will notice that there is one row. So the number of rows in this matrix is 1 and the number of columns is 4. So the order of this matrix is given by 1, because there's 1 row, by 4 columns. Such a matrix is called a row matrix. So let us define a row matrix. Row matrix is a matrix which has just 1 row, right? So the number of columns could be anything, but the number of rows is always 1 in case of a row matrix. Let us take a look at the matrix B. B is arranged. There are 3 numbers which are arranged vertically. The number of columns here is 1. The number of rows is 3. This is the first row. This is the second row. This is the third row. So the order of this matrix is given by 3 by 1. The number of rows could be anything, but if the number of columns is 1, such a matrix is called column matrix. Okay. So let us define a column matrix. Column matrix is that matrix which has 1 column in it. The number of rows could be n. Let's take a look at the matrix C. So matrix C over here has 2 rows. You will notice that there are 2 rows and there are 3 columns. So this is row 1 and row 2. And there are 3 columns. Let's name them C1, C2 and C3. Therefore, you will notice that this matrix has 2 rows and 3 columns. Therefore, the order of this matrix is 2 by 3. Such a matrix is called rectangular matrix, where the number of rows and columns don't match with each other. Okay. So rectangular matrix is a matrix where the number of rows and the number of columns don't match with each other. So there has to be something known as a square matrix, right? This tells us that there has to be a matrix which is also known as square matrix. So consider the matrix E, which is written as 2, 1, 3, 5, minus 8, 0, 2, half, 1/3. In this particular matrix E, you will notice that there are 3 rows, row 1, row 2 and row 3. And there are 3 columns, that's C1, C2 and C3. The order of this matrix is 3 by 3, and such a matrix where the number of rows is equal to the number of columns, such a matrix is called square matrix. Okay, so square matrix is that matrix where the number of rows is equal to the number of columns. Let us now take a look at the matrix D. In the matrix D, you will notice that all the elements are 0. So what is the order of this matrix? The order of this matrix is there are 2 rows, row 1 and row 2, and there are 4 columns, 1, 2, 3 and 4. Therefore, the order of this matrix is 2 rows by 4 columns, but all the entries in this matrix are 0. Such a matrix is called a null matrix or a 0 matrix, or it is also called an empty matrix. Okay. So the most commonly used words are null matrix and 0 matrix. In such matrices, all the elements are 0. So now let us continue with some more types of matrices. Matrix for this. So null matrix and 0 matrix is the right name for matrices where all the elements are 0. So now let us take some more types of matrices. So we defined the square matrix as that matrix with equal number of rows and columns. So let's write a few square matrices. This is a square matrix of order 3 by 3. Now because we know that the number of rows is always equal to the number of columns, we just say that this is a square matrix. This is a square matrix of order 3, right? We don't mention the 3 by 3 because it's a square matrix. It is presumed that the number of rows have to be equal to the number of columns. Let's try to write a few more square matrices and let's see what's unique about each of those. In this particular matrix, you will notice that the diagonal element, so in matrix there exists just one diagonal, which is the left top to the right bottom, right? So diagonal is possible only in case of a square matrix. In case of rectangular matrix, it's not possible. So the diagonal elements of this matrix are not 0, whereas all the other elements are 0, and that is why such a matrix is called a diagonal matrix. Okay, so a diagonal matrix happens to be a square matrix. So is a square matrix with all the non-diagonal elements equal to 0. Such a matrix is called a diagonal matrix. Now the diagonal elements could be anything. Again, just to show you the diagonal always stretches from the left top to the right bottom, right? So this is the only diagonal that is present in a diagonal matrix, and that's why such matrices can also be represented as diag 2, 12 and 8. So this tells me that the diagonal elements are 2, 12 and 8, and of course based on the number of entries in the diagonal matrix, it also tells me the order of the matrix. So for example, if somebody says matrix B is diag of root 3, root 2, root 5 and root 7, what this means is the diagonal elements are root 3, root 2, root 5 and root 7, and all the other elements, so the order of this matrix is 4 by 4, all the other elements are 0, right? So that's why writing this as diag of root 3, root 2, root 5 and root 7 would be a shorter way of representing this particular matrix. So such matrices are called diagonal matrices. Now let's take up the scalar matrices. So consider the matrix that is shown on the board right now. You will notice that this is a diagonal matrix because the diagonal elements are non-zero and all the other elements are 0. There is something that's even more specific. You will notice that all diagonal elements are equal to each other, right? And such elements are called scalar, or such matrices are called scalar matrices, right? So this is a scalar matrix. So a scalar matrix is basically a diagonal matrix. I would define scalar matrix as a diagonal matrix with all the diagonal elements equal. Now because it's a diagonal matrix, of course scalar matrix has to be a square matrix because every diagonal matrix is a square matrix. Therefore scalar matrices are also square matrices with all their diagonal elements equal. Now if this equal element, or if the elements along the diagonal in a scalar matrix happen to be 1, so what I'm trying to say is, suppose we have a matrix which is written as follows: 1 0 0 0 1 0 0 0 1, right? So this, in this particular matrix, this is definitely a scalar matrix. Why is it a scalar matrix? It is a scalar matrix because the diagonal elements are all equal, and of course it's a diagonal matrix because the non-diagonal elements are 0. More importantly, the diagonal elements are equal to 1. That is why such matrices are called as, so scalar matrix with diagonal elements equal to 1, with diagonal element equal to 1, such matrices are called unit matrices. We call them unit matrices or identity matrices, right? So identity matrix is a matrix with all its diagonal elements 1, Now, of course, there can be different orders for the identity matrix. So let us list down a few identity matrices. I'll just pause for a minute so that you can take a look at all these different types, and then we shall continue. So take a look at these three matrices. You will notice that all of them are identity matrices because the diagonal elements are 1 and all the other elements are 0, right? So the first identity matrix that you have is an identity matrix with order 2. So there are 2 rows and 2 columns. That is why it is represented by I2. The second matrix is an identity matrix of order 3, which is why there are 3 rows and 3 columns. That's why it is represented by I3. And then you have an identity matrix with 4 rows and 4 columns. So this would be represented by I4, right? So identity matrices can be of any order. Of course, it's a square matrix with the diagonal elements equal to 1. Generally, the letter I is reserved for the identity matrix, and the letter O is reserved for the zero matrix, right? So zero matrix was a matrix where all the elements were 0, and they were also called as null matrices. So we will use the other letters for representing matrices. These 2 letters are generally reserved for these special matrices. So now we are going to deal with the next concept in matrices, which is equality of matrices. Let us consider that I am writing a matrix like this: 1, 3, 2, 5, 6, 9. Okay. Now, before we understand the concept of equality of matrices, let's understand the positioning of these elements. So, what is the order of this particular matrix? There are 2 rows and there are 3 columns. Therefore, the order of this matrix is 2 by 3, right? Now let's look at the element 1. Element 1 is the element in the first row and first column, which is why I would represent this position by, so let me do one thing. Let me write the relative positions just below this matrix. The element 1 would be the element in the first row. So I would represent it by A1, 1. Where the first number represents the row number and the second number represents the column number. So this element 1 is actually A11. Let's see what is element 3. Element 3 falls in the first row and the second column. That's why this element is A, first row, second column. So that's A12. The element 2 falls in the first row and the third column. So this is A13, right? Similarly, the element 5 falls in the second row. You will notice that 5 is in the second row. So it would be A, second row. The element 6 falls in the second row. So I would write element 6 as the position is second row and second column. And the position of element 9 is second row, third column, right? So this is how we always label the position of all the elements in this matrix. So for example, if somebody said, let me find A31, what it means is I am finding the element in the third row and first column, right? That is the position of this particular element. Similarly, if somebody says find A42, what this means is find the element in the fourth row and second column. Okay, so this is how we address the different elements that are there in a matrix. Now let's define what is meant by equality of matrices. So two matrices are said to be equal if first they have the same order, and second, each element of the two matrices should match. So let us take some examples of matrices and see whether they are equal or not. So consider the two matrices A and B here. Let us first check their order. The order of these matrices are, there are 3 rows and there is 1 column. So this matrix is 3 by 1 and this matrix is also a 3 by 1 matrix. The orders are equal to each other. Okay, so the first checkpoint is complete. Now let's look at the corresponding elements. I have a 3 in first row, first column. So my A11 first row, first column is 3, whereas my A11 in this case is 2. The two elements don't match with each other, which is why these two matrices are not equal. Okay, let's take one more example. Let's consider these two matrices, matrix B and matrix C. Let us take a look at the order of these two matrices. There is 1 row in both the matrices and there are 3 columns. So let me split these columns by the dotted lines, right? So there are 3 columns, there are 3 columns and 1 row. So the order of this matrix is 1 by 3. Whereas in this case also there is 1 row and there are 3 columns. So the order of this matrix is also 1 by 3. We should notice that such matrices are called row matrices where there is just 1 row. Now so the order matches. Now let's take a look at their individual elements. I have sine square theta plus cos square theta. If I know my trigonometry, I know that sine square plus cos square is 1. So the first 2 elements definitely match. Let's take a look at the second element. In matrix B, the second element is sine square theta by cos square theta. And in matrix C, it is tan square theta. So sine square theta by cos square theta is indeed equal to tan square theta. And the third element that I have is 3 square, which is equal to 9. So you will notice that though these elements have been written in different forms, their meaning is entirely the same. So each element actually is equal to the corresponding element in the second matrix, and that is why these matrices are equal matrices. So whenever we equate two matrices, we have to understand that their corresponding elements should be equal. So for example, if I take a 2 by 2 matrix as follows. So I take this is one 2 by 2 matrix and I equate this to the following. Then what can be done is I can equate the corresponding elements. What I mean by that is the element x, which is the first row, first column, should be equal to negative 8. So I can say x is equal to minus 8. Then the first row, second column element, that is the element in the rectangle right now, should be equal to the first row, second column, which means that y plus 2 should be equal to 4, and this implies y has to be equal to 2. Similarly, the element in the second row, first column, that is this 2, should be equal to the second row first column element, which is Z, which means that I can say Z is equal to 2, and the element in the second row second column they both have to be equal to each other, which means 3s should be equal to 15, and therefore s should be equal to 5. So when we have two matrices equal to each other, we should remember that their corresponding elements have to be equal, and two matrices can be equal only when their order is equal. And if they're telling you that the matrices are equal, then you can definitely equate the corresponding elements. Okay, so I'll just pause for a couple of seconds for you to grasp this, and then I will continue. So let us now turn our attention to addition and subtraction of two or more matrices. We can add and subtract two or more matrices only when their orders are equal. So the necessary condition for addition or subtraction to be possible is, the orders of the matrices that are taking part in the operation should be equal. So what I mean to say is, let us consider addition of two matrices. So let's assume I am adding 3, 2, 1, 5 with another matrix which is 4, 2. Now the problem here is the order of the two matrices is not equal. So I cannot decide whether I should add this 3 with 4 because this is the first row first column element. This is also the first row first column element. So if I add 3 with 4, then there is no number left for this 2 to be added with. That is why the order of the two matrices should be equal. So when we add or subtract matrices, we add or subtract the corresponding elements, right? So let us see another combination of matrix. Let me add 3, 4, 2, minus 5 with 6, 4, 3, minus 8. So when I add these two matrices, what I'm going to do is, I'm going to add the corresponding elements, meaning I will take the first row first column element of the first matrix and add it with the first row first column element of the second matrix. So 3 plus 6 is going to be 9. 4 plus 4, I am taking the first row second column matrix and adding it with the first row second column matrix. So 4 plus 4 will be 8. Then, okay, let me shade it. I think with shading it will get better. So I add these two. Then let me add the element 2 with the element 3. Because those elements are the elements in the second row and first column. Right, so these are the two corresponding elements, their positions correspond. So 2 plus 3 would be 5 and negative 5 plus negative 8 would be negative 13. So this is how we add or subtract two matrices, and that is why it is necessary that the matrices which get added or subtracted should have the same order. Subtraction also works in the similar way. So now let's take a problem with subtraction. Suppose I have 3, 2, 5, 9 minus 3, 2, 6, 11. Now let us see how to subtract. Again, I start subtracting. The first thing that I check is whether the orders are same. The orders are 2 by 2 in both the matrices. So I can now start subtracting the corresponding elements. So 3 minus 3 gives me a 0. 2 minus 2 gives me a 0. 5 minus 6 gives me minus 1. And 9 minus 11 gives me minus 2. So the resulting matrix is of the same order as the two matrices which you are either adding or subtracting. So let us now note down some key points about addition and subtraction. So the first important point is the orders of the participating matrices in addition or subtraction should be equal to each other. So this is a necessary condition. This is a necessary condition for addition or subtraction to be even possible. The next important point is we add or subtract the elements whose positions correspond, meaning I will take the element with first row and first column position of one matrix and I will perform the operation on the first row and first column element of some other matrix, whether it is addition or subtraction. So we always add or subtract the elements whose positions correspond to each other. The third and important point is be careful with the signs. So especially when you are adding and subtracting and when you have these negative numbers, you have combinations of negative numbers and positive numbers, you have to be really careful with the signs when you are going to add or subtract these matrices. And maximum mistakes will happen in this particular procedure where you don't tend to honor the signs and perform the operations correctly. So this is how you add or subtract two or more matrices. And now let us take some questions based on addition and subtraction of matrices. So let us consider these two examples. In the first example, you will notice that the matrices are being subtracted, whereas in the second example, you will notice that there is a combination of addition and subtraction. So let's take up the first question. Here I have the order of the two matrices matches. Both the matrices are of the order 2 by 3. So I am going to take up the individual elements and subtract 3 minus 2. So that's 3 minus 2. 2 minus 1. So let's write that 2 minus 1. 4 minus 4. Then I'm taking the elements from the second row, the first column element, 1 minus of, and this is where you have to be careful, 1 minus of minus 6. Then I have minus 1 minus of minus 5. And then I have 3 minus 0. So therefore what I get is 3 minus 2 is 1, 2 minus 1 is 1, 4 minus 4 is 0. This is 1 plus 6, which is 7. This is minus 1 plus 5, which is 4. And 3 minus 0 is 3. And therefore the order of the resulting matrix is same as the order of the two matrices. And this is how we will perform the operation of subtraction. Let us now take up the second question, which contains a combination of addition and subtraction. So we have all the orders match. So all the orders are 2 by 3. All the matrices are of order 2 by 3. So now let us take the corresponding elements and combine. I have minus 3, that's the first row, first column, plus 4, minus 1. So what I've done is I've taken the first row, first column elements of all the three matrices, right? And I've honored the signs also. So be very careful with the signs. Then I have 4 plus of minus 4, that's minus 4, minus 0. Then let's take a look at the next element. The next element would be 2 plus 3 minus 5. Then second row, first column. So let us mark all the elements. So it is negative 5 plus 2 minus of minus 3. Then let's take the second column, second row, second column element, minus 1 plus 1 minus 0. And then the second row, third column, that's 0 plus 0 minus 0, right? So you will notice that all these elements are 0. Minus 3 plus 4 minus 1 is 0. 4 minus 4 minus 0 is 0. 2 plus 3 is 5. 5 minus 5 is 0. Negative 5 plus 2 is negative 3. And negative 3 positive 3 is also 0. Negative 1 positive 1 is 0. And addition of all zeros is 0. Therefore, this is a null matrix, right? So this is how we perform addition and subtraction of matrices. Now we will go ahead and understand the multiplication of a matrix by a scalar value. And let me pause for a couple of seconds and then we Okay, moving on. So when it comes to multiplication of a matrix can be done with a scalar quantity. A scalar quantity would mean a single number or a variable or a single value which gets multiplied with the matrix, or a matrix could be multiplied with another matrix itself. So these are the two types of multiplication of a matrix that is possible. And in this particular section, we are going to focus on how to multiply a matrix with a scalar value. And in a different video, we will find out how to multiply a matrix with a matrix. So when I say that I want to multiply a matrix with a scalar value, let's consider that a matrix A is 3, 4, 2, 9. Now, if I want to find 9a, okay, so 9a basically means 9 multiplied by a. So 9 multiplied by a, so we know that multiplication is repeated addition. So 9a can be written as a plus a plus a plus a, and this is going to happen 9 times, right? And now I know that I know how to add matrices. So it would be 3, 4, 2, 9 plus 3, 4, 2, 9, and this is going to happen 9 times, right? So 3, 4, 2, 9. I'm going to add the individual elements. So 3 plus 3 plus 3, and you will notice that 3 gets added 9 times, which is equivalent to multiplying 3 by 9. Similarly, the element 4 also gets added 9 times. So 4 plus 4 plus 4, and this goes on for 9 times. So that is equivalent to 4 multiplied by 9. Similarly, the element 2 also gets added 9 times, which means it is 2 multiplied by 9. And then the last element is also going to be 9 added 9 times, that is 9 multiplied by 9. So what happens is, when you're trying to find 9 times A, what has actually happened is each individual element of this matrix is getting multiplied by 9. So that means 9A is going to be 27, 36, 18 and 81. Therefore, when you multiply a matrix with any scalar value, by the way, this number with which you are multiplying the matrix with, it could be positive, it could be negative, it could be rational, irrational, it could be an algebraic term, it could be a monomial, it could be a binomial, and so on, right? So whatever you multiply with the matrix, each element of the matrix gets multiplied with the same value. Okay, so this is how you multiply a matrix with a scalar quantity. Let me give you a few examples to explain this particular idea. So consider the matrix A, which is as shown on the board. We know that the order of this matrix is 2 by 2. If I want to find 3A, 3A basically means 3 multiplied with A. So 3 multiplied by the matrix which is given. And now what is going to happen is I am going to multiply the matrix, each element with the number 3. So 3 into 3 root 3 becomes 9 root 3. 3 into root 3 becomes 3 root 3. 3 into minus 5 root 3 becomes minus 15 root 3. And 3 into 2 root 3 becomes 6 root 3. Right? So this is how I find the value of 3A. Let me now go ahead and find the value of minus root 3 times A. So minus root 3 times A would mean minus root 3 multiplied by the matrix A, which is 3 root 3, root 3, minus 5 root 3 and 2 root 3. So now let me start multiplying the element with each element inside the matrix. So minus root 3 into 3 root 3, let's find that out. Let's write it minus root 3 multiplied by 3 root 3. Then minus root 3 multiplied by root 3. So that's minus root 3 multiplied by root 3. Then I have minus root 3 multiplied by minus 5 root 3. And then minus root 3 multiplied by 2 root 3. Minus root 3 multiplied by 2 root 3. Therefore, on combining all these elements, what I get is root 3 into root 3 is 3 and 3 into 3 is 9. So the first element is minus 9. Be careful with the signs. Root 3 into root 3 is 3. So this becomes minus 3. Minus into minus is plus. So plus root 3 into root 3 is 3. 3 multiplied by 5 is 15. And minus into plus is minus. Root 3's are 3. 3 2's are 6. So this is how I get the value of minus root 3 times A. Let us now continue with the C subpart, which is 1 by root 3 times A. So 1 by root 3 times A becomes 1 by root 3 times 3 root 3, root 3, minus 5 root 3 and 2 root 3. So what I'm going to do is I'm going to multiply 1 by root 3 with each element. So this becomes 3 root 3 upon root 3. Then root 3 upon root 3. So basically multiplying by 1 by root 3 means each element is getting divided by root 3. Then I have minus 5 root 3 by root 3 and 2 root 3 by root 3. So now some cancellations are possible. So let's start cancellation. Root 3 cancels, root 3 cancels, root 3 cancels to 1. And root 3 cancels. So what I get is 3, 1, negative 5 and positive 2. Therefore, 1 by root 3A becomes the following matrix. Let me pause for a couple of seconds so that I can erase some part of the board to solve my D section. In the meanwhile, you could also try solving the D section and I will give you the answer and you can check your answer. So okay, in case you have figured out the answer, let's check your answer. So minus 4a would mean minus 4 multiplied by a. A is 3 root 3 root 3 minus 5 root 3 and 2 root 3. Let's multiply each element with minus 4. So what I get is minus 12 root 3 minus 4 root 3. Minus into minus is positive. 4 5s are 20. So this is positive 20 root 3 and minus 8 root 3. This is the final answer. So I hope your answer did match mine. And I'll again pause for a few seconds, and then we will take up some problems on Okay, let us consider these two problems. I have to simplify this particular set of matrices. So 3 multiplied by the first matrix. I know that when I multiply matrix with a scalar quantity, I should multiply each element with the constant. So 3 4s are 12, 3 2s are 6, 3 into minus 3 is minus 9, and 3 8s are 24, plus 4 times 4 into minus 4 is minus 16, 4 into minus 2 is minus 8, 4 3s are 12, and 4 into minus 3 is minus 12. Let me keep the minus sign as it is, and let me only shift the 2 inside and multiply all the terms. So let's leave the subtraction sign as is. 2 4s are 8, 2 1s are 2, 2 zeros are 0, and 2 zeros are 0. And now let's go ahead with the addition and subtraction. So 12, I have to add or subtract the corresponding rows. So corresponding elements. So 12 plus of minus 16, that's 12 minus 16, minus 8. That's the first row, first column. Then 6 plus of minus 8, that's minus 8, be very careful, minus 2. Then I have minus 9 plus 12 minus 0, and I have 24 plus of minus 12, which is minus 12 minus 0, and therefore the value of the matrix is 12 minus 16 is minus 4 minus 8 is minus 12, 6 minus 8 is minus 2 minus 2 minus 2 is minus 4, minus 9 plus 12 is 3, and 24 minus 12 is 12. Therefore, this is my final answer. I have applied all the rules of matrix addition and subtraction here, as well as multiplication of a matrix by a scalar quantity. Now let us take a look at the second question, which is find the matrix x if 3x equals, so the matrix 3x equals 2 times 6 2 4 5 minus 9 1 negative 4 negative 2. So now let's see how to solve this problem. First of all, I should multiply this 2 with all the elements. So 2 6 are 12. Again, laws of BODMAS also apply to matrices. So multiplication before subtraction. 2 6 are 12, 2 2s are 4, 2 4s are 8, and 2 5s are 10, minus 9 1 negative 4 negative 2. So now I am going to perform subtraction. So 3x therefore equals, let's take the corresponding elements and subtract. 12 minus 9, 4 minus 1, 8 minus of minus 4, and 10 minus of minus 2 is what I have. And therefore 3x becomes equal to 12 minus 9 is 3, 8 plus 4 is 12, 4 minus 1 is 3, 10 plus 2 is also 12. Now 3 is in multiplication with x, therefore on the other side 3 will go down to division. So it becomes 1/3 of 3, 3, 12, 12, which is equal to 1/3 of 3 is 1. Again, so what I am doing is I am multiplying this 1/3 with every element. So 1/3 into 3 is 1. 1/3 into 3 is also 1. 1 by 3 12s are. So 1 by 3 into 12 is 4 and 1/3 of 12 is again 4. So the matrix is 1 1 4 4. So in these two problems we have applied the concepts of matrices that we have learned so far, and we will deal with some more problems in the next segment on matrices. I will pause for a few seconds and then we will conclude this. Okay, let's conclude this session.